Welcome to Ask and Learn.
We are going to talk about atomic transitions. So let's remember that atomic transitions can occur in two different mechanisms. So the first mechanism I'm going to talk about is absorption. And absorption basically means that is a transition that happens from ground state. So let's write here. And this is an important thing. Absorption always starts from the ground state. To a higher state. And the emission mechanism happens when we have transitions from higher states to lower ones. Okay? So in this exercise, we know that the absorption spectrum of an atom is consists of three wavelengths. The first wavelength, I'm going to call lambda 1, has 200 nanometers. The second wavelength of this atom absorption spectrum is 300 nanometers. And the last wavelength is 400 nanometers. And the exercise wants us to use this information to draw the energy diagram of this atom. So we know that this is the photons from the absorption. So absorption, we know that starts from the ground state. So this means that the energy transition that requires these types of photons are the following. So the transitions to a higher state that I'm going to call N minus the energy of the ground state, which is usually 0. And in this case, I'm going to assume it's 0 electronvolts. And through energy conservation, we know that the energy of the transition is going to be equal to the energy of the absorbed photon. And the energy of the photon is Planck's constant times c divided by lambda. So first, let's calculate the energy from the first photon. So the transition energy for the first photon is going to be Hc divided by 200 nanometers. So I'm going to write Planck's constant here, so 4.136 times 10 to the minus 15 electron volts times seconds times the speed of the light divided by 200 nanometers. So we're going to find that this first transition corresponds to an excited state that has an energy of 6.2 electron volts. Now, for the second absorption, we're going to do the same thing. So Hc divided by 300 nanometers. And this is going to be equal to an energy of 4.13 electron volts. And the third transition corresponds to this energy, which is equal to 2.48 electronvolts. So we can see that this is the first excited state, so I'm going to call this E2. This is the third excited state, I'm going to call E3, and this is going to be, this is the first, this is the second excited state, and this is the third excited state. That corresponds to the level 4. On which, again, I'm assuming that the level 1, the ground state, is 0 electron volts. Now we are ready to draw the energy diagram. So let's put the lines here. So 4 lines for the 4 energy levels. The first line corresponds to n equal to 1 and is the ground state. So the energy here is 0 electron volts. The second line is n equal to 2, the first excited state, 2.48 electron volts. The third line is the second excited state, 4.13 electron volts. And the fourth line is the third excited state, which is 6.2 electron volts. Now, question B wants us to calculate the emission wavelengths for this atom. So remember that emission is from higher states to any lower states. So first, let's see the emission let's see what types of emissions we can have. We can have a transition from this state to this state, from 4 to 3. We can have from 4 to 2, and from 4 to the ground state. We can also have from the state 3 to state 2, and from state 3 directly to the ground state, and we can also have from the first excited state to the ground state. So you can see that we can have 6 photons from the transitions from the emission spectrum. So let's calculate each one of those. So the wavelength of the photon from this transition for 3 is going to be equal to hc divided by the energy of the transition, where the energy of the transition in this case is going to be the energy of state 4 minus the energy of state 3. So let's write here. So Planck's constant electron volts times seconds times the speed of the light divided by the difference between the highest state with the second excited state. This is going to be equal to 600 nanometers. Now, to the next transition is the transition from 4 to 2. So again, it's the same thing, hc divided by the difference between the energy of these levels. So 6.2 electron volts minus 2.48 electron volts, which is going to give us a photon with 333 nanometers of wavelength. So for the transition 4-1, Hc divided by 6.2 electron volts minus the energy of the ground state, which is 0. This is equal to 200 nanometers. Now, the wavelength for the transition from the state 3 to state 2, which is this arrow here, Hc divided by 4.13 eV minus 2.48 eV. This is equal to 751 nanometers. Then from the third state to the ground state, Hc divided by 4.13 eV, which is 300 nanometers. And lastly is the photon from the transition of the first excited state to the ground state. Lambda, So lambda 2.1 Hc divided by 2.48 electron volts. And this is equal to 500 nanometers.